Hello, Matt here from chemistrystudent.com. In this video, we're going to look at the acylation of benzene. We're going to talk about what the acylation of benzene actually is, outline the steps in the mechanism for the reaction, and look at why a halogen carrier catalyst is needed. The structure of benzene and the other reactions of benzene, including alkylation, are outlined in separate videos. Check the links in the description below. Before we talk in detail about the acylation of benzene, there are a few essential ideas you need to be comfortable with. Benzene is a cyclic hydrocarbon with a delocalized electron system that reacts with strong electrophiles in electrophilic substitution reactions. It is essential you are comfortable with this general mechanism in order to follow the rest of this video. If unsure, please check the link in the description below for the video that outlines this. Electrophiles are electron pair acceptors. They are usually positively charged and are attracted to areas of high electron density. A substitution reaction is where one group or atom in a molecule is swapped for another group. Acyl chlorides are compounds that have a functional group consisting of a carbon atom, single bonded to a chlorine atom, and double bonded to an oxygen atom. They are highly reactive due to the polar carbon-oxygen bond and carbon-chlorine bond. Both oxygen and chlorine are highly electronegative and so pull electron density away from the carbon atom towards themselves, leaving the carbon atom with a partial positive charge that's quite large. This all makes the carbon-chlorine bond weak as a result, and if given a little nudge, it can break, leaving a positively charged carbon atom behind, creating what we call an acyl ion. An acyl group refers to a carbon chain, alkyl group, with a carbonyl C double bond O on the end. So, recap done, let's go. When benzene undergoes an acylation reaction, an acyl group, usually from an acyl chloride molecule, is swapped or substituted for a hydrogen bonded to a carbon atom. An aromatic ketone is produced. The type of mechanism occurring is electrophilic substitution and follows a standard mechanism. This particular mechanism pathway was discovered in the 19th century by two chemists called Friedel and Crafts. As a result, it is referred to as the Friedel-Crafts acylation. The alkylation of benzene follows a virtually identical pathway and is also considered a Friedel-Crafts reaction. That reaction has been covered in a different video. Check the link in the description below. At this level, I think it's probably easier for you to just refer to the two reactions as acylation and alkylation to make sure you got them separate in your head. I'm sure Friedel and Kraft wouldn't have taken any offense. Acyl chlorides are a great source of acyl groups in organic chemistry and, as mentioned in the recap, can quite easily be nudged into forming acyl ions that can act as electrophiles. To give this nudge and weaken the carbon-chlorine bond to the point of breaking, a catalyst is used. The carbon-chlorine bond in an acyl chloride is already highly polar, as the oxygen and chlorine atoms bonded to the carbon both pull the electron density towards themselves. Because the chlorine is essentially fighting oxygen in a tug of war, it doesn't quite get as much electron density as it would like. To pull the electron density even more towards the partially negative chlorine, a halogen carrier is used. A halogen carrier basically just means a metal, usually iron or aluminium, that is bonded to atoms of the halogen in question, in this case chlorine. Aluminium trichloride will be used for this example, although you may also see iron trichloride being used as well. A lone pair of electrons on the partially negative chlorine in the acyl chloride get attracted to the metal in the halogen carrier and tries to form a coordinate bond. Note it's a coordinate bond as both the electrons are coming from one atom, the chlorine. This means the chlorine atom has lost some of its electron density. To try and get it back from somewhere, it pulls the electrons in the carbon-chlorine bond towards itself even more, creating a very polar bond and is significantly weakening the bond to the point of breaking, effectively forming an acyl ion with a carbon atom that has a positive charge. This carbon atom is now sufficiently electron deficient to act as an electrophile and is able to react with benzene. The reaction with benzene now just proceeds as expected, a standard electrophilic substitution. To get things started, the reaction mixture is heated. A pair of electrons from the delocalized ring of electrons in benzene is used to form a bond between a carbon atom in the ring to the positive carbon atom in the acyl ion. This breaks open the ring of delocalized electrons and forms an unstable intermediate. To reform a full ring and get back to some stability, the carbon-hydrogen bond on the same carbon as the carbon acyl group breaks. The electron pair is put back into the delocalized system and a H+ ion is removed by a chlorine atom from the halogen carrier intermediate just formed. This leads to the formation of an aromatic ketone, HCl, and the reforming of the original halogen carrier, aluminium trichloride. This is why the halogen carrier is acting as a catalyst as it gets reformed at the end of the reaction. So, to summarize, benzene reacts with acyl chlorides in the presence of a halogen carrier catalyst to form aromatic ketones. The reaction is an example of electrophilic substitution, and a halogen carrier catalyst is needed to help create the acylium ion electrophile needed to start the reaction. This specific type of electrophilic substitution is referred to as a Friedel-Crafts acylation. I hope you found this video useful. Please check out other relevant videos in the links given in the description below, and visit chemistrystudent.com for free notes and revision materials.